SwayamPrabha. Digital India. Educated India.
Okay, I think we can start. We have an hour and a half. By the way, some of you approached me at the end and asked me some very good questions. I think it's better if you ask those questions during the class, because some of them, I mean, if you have a specific question to your application, please, by all means, always come to me. But some of the questions you asked were very good, so it's actually a good idea that people hear the answer about it, because many people may have the same questions in that sense. I could actually. So I mean, there were several of them. For example, someone asked me, okay, how do you implement the history field in the phase field UMAT code that you saw in Abacus? There was no history field, right? So the way you will do it, Abacus has I eliminated that line of code. It's in our website, but I eliminated that line of code just to make it easier for people to see the simplest code. But this extra line will be a line where you have Abacus allows you in the UMAT to have state variables, which are variables that you can keep in there and accumulate and call. So you will store in that state variable the strength and the density of the previous increment, and then you will compare. It will be, you take the maximum of 2, and that continues along. So just one line of code, for example. So there's multiple options like this. By the way, the codes are all in the website, so you can already download them and try to run them and see whether you like them or not. And if you have any questions, come by, of course. So yeah, before it was all about the implementation. You saw that the implementation is relatively easy. So the phase field is like a variable that you solve for, like displacements, like temperature. You solve that equation, and that tells you a distribution of the phase field 0 and 1 in the space, in time. And that 0, 1 will determine whether you have cracks, uncracked, or fully cracked material points. So that's the idea. So very simple to implement, very easy, and very robust. And I gave you some tricks on how to deal with convergence issues if you ever encounter them. So now let's look at applications. And I have listed a number of applications. I don't know how much time we will have. I think for today I had 4 applications in mind. Let me see if this works. Yeah, so we have until 12:30, so I have 4 applications in mind. Let's see, otherwise we can see them, of course, tomorrow as well. So the 4 that I have thought to discuss, these are not the ones that I've been working the most. For those I've dedicated special sessions like hydrogen, corrosion, batteries. But these are some where we had a lot of fun and what I thought were interesting. One is related to kind of a smart or shape memory materials. We also do quite a lot of work in fracture in glaciology. All of these are phase field fracture applications. For example, in shape memory materials, or one could use a phase field also to describe the phase change. But I'm going to talk about fracture only. Hydraulic fracture, I know some of you have an interest here, and then composites, including functionally graded materials, and also carbon nanotube composites, not only fiber reinforced composites. So let me start with the smart shape memory materials. I don't know if you're all familiar with this. Have you all heard about what a shape memory material is before? I think so. For those of you who have not, this video I think is quite a nice illustration. So these are materials who undergo phase change and therefore can recover their original shape upon application of temperature of a mechanical load. You can see here a clip that this is first a wire. You deform that wire and then you heat that wire and it recovers its original shape. And you see something here that looks more like a clip, so you deform that clip, then you apply a temperature, and you see it recovers original shape. And these things happens because of transformation of phase between austenite and martensite. I mean, there's many types of shape memory materials, but I'm going to focus on shape memory alloys. A typical example is nitinol. There are others. And there's 2 phenomena associated with this. One is what we call the superelasticity effect, and the other one is what we call the shape memory effect. And you can see them here. So this is the stress-strain curve. And this is called superelasticity because, as you can see here, so this is stress-strain curve, and you can map it here. So I'm in point 1, which means this is stress versus temperature. I'm going to move through here. This is the superelasticity effect. So I'm not going to change temperature for the time being. So I'm in point 1. If I increase my load, I'm starting austenite, and then eventually, when I get to point 2, so everything is linear elastic. It's an austenite behavior, all linear elastic. When I get to point 2, I start this transformation stress. I reach this threshold stress where the phase transformation starts. I get this kind of non-linear behavior. I haven't still reached plasticity. The yield limit will be somewhere here. So I still get some sort of phase transformation. So I get some sort of non-linear behavior. And then when I get to 3, I'm in this fully martensite region. And if I keep increasing my load, then eventually I'll become elastic here, and then I'll get some sort of yielding or somewhere here. But if I unload from here, you can see that I go back, Was this not working well, or did I lose internet? I do have internet. So I'll continue here then. So you can see that you know, if you go down, if you unload, you go back to 3 to 4. At 4, you start this transformation from martensite to austenite, and then when you get to 5, you're getting fully austenite. And what you see, you know, this is different from what you're expected to see, right? Those of you working with metals will immediately see that when you have a stress-strain curve, you do something like this, you get into this non-linear regime, this elastoplastic regime, and then when you unload elastically, but you are left with that plastic strain, that reversible strain. So this is different. You see that you recovered all the strains. So this can be actually quite large strains. I'm trying to remember now, 10%, something along those lines. So this makes them suitable for some applications where you really want to have very large deformations, but you don't want to have irreversible deformations. That's the idea. So yeah, this is the phenomenon. And this happens just because these kind of non-linear deformations are a result of a phase transformation. And then the other effect is the chemo-mechanical effect, where you have the same situation. Maybe you start somewhere here. So you very quickly go from A to B. So you start at a lower temperature. So you see, this is the difference between these two. This is the temperature that is above this austenitic phase transformation temperature, or below below that temperature. So you start going up from B to C. You start transforming to martensite. Then you get to C fully transformed, and then you unload and you have some remaining left. But then if you apply a temperature, you can take it all the way to austenite. This is what we saw in those videos. You apply a load, you have something that is irreversibly deformed here, but then if I apply a temperature, I can go back from C to A, basically. You move in this direction, and you go back to austenite, and you recover your original position. That's the idea. So these are the two phenomena. And in the context of fracture mechanics, the implications are that, of course, stresses are very large in your crack tip, so you're going to be moving around those lines, right? So you're going to have something that is austenite outside of your crack. Well, it depends on your temperature, but let's say we're somewhere here. Austenite far away from your crack. And then as you approach the crack tip, you're going to have a phase transformation. You have a region where you have both austenite and martensite. And then when you reach a certain stress, you're going to have mostly martensite. And you could also have plasticity, but it will be very, very localized, because the plasticity threshold is somewhere here. So you have to go quite high. So you have a bit of plasticity, but it's quite localized. We haven't modeled the plasticity. Some other groups have done, but it's not a key effect. Yeah, so this is what it looks like. You can see here. This is the martensite phase fraction variable. So it's equal to 0 in the austenite region. Then it becomes between 0 and 1, and then it becomes fully 1. So this is a state variable. Again, you can use phase field to model also this phase transformation, so you can model this thing with phase field. But we're only going to model for cracks for the time being. And you can see, if you plot the log-log plot of the stresses ahead of the crack tip, is something like this. And remember what we discussed in the first lecture. Linear elasticity has a square root singularity. So you see the square root singularity of linear elasticity. Then you have this transformation zone. And then you have this linear elastic zone that is related to the fully martensite regime. So in terms of fracture, what happens is that these sort of non-linear strains that are related to this transformation, they add a little bit of plasticity, so they bring some toughening effect. So when we do fracture experiments on this nitinol and other shear memory alloys, what we see is that there is a toughening effect, that the R curve, even though we haven't reached maybe much of plasticity, the R curve is not flat, like it would be a linear elastic material. We actually see a bit of plastic dissipation, less than with plasticity, but a little bit due to those inelastic transformation strains. We call them transformation strains. So there's some transformation work that creates some toughening effects. So basically, we wanted to see whether phase field was able to capture that, and we didn't want to define things. So the beauty of the model is that it can capture things naturally. So you don't have to do anything. The only thing we did was we changed the constitutive relationships to define the usual shear memory relationships. There are various models. I think we use both the Lagoudas model, but also the one of Auricio model. There's two models, Auricio model, Sousa and Auricio, and the Lagoudas model. So we use both of those models. But they're basically constitutive models. You can think of them as plasticity, basically. And this is what you get. So we run the simulation. This is the same square plate that I showed you before. Remember, the square plate, the behavior was such that the force increased, and eventually, boom, you get this kind of big drop. This was linear elasticity. Now we don't do anything to the phase field. And there's a bit of a discussion on what you do with the driving force. Do you consider the elastic strain density as the driving force, or the elastic plus some component of this transformation extraordinary density. But anyway, let's leave that aside for the moment. When you do that, you just add the shape memory behavior, and you can see that you get this kind of toughening effect. No longer you have something that is super brittle. You get a bit of a stable crack growth, some sort of propagation here, where you can see, I'm plotting here the facial fracture. You can see how it changes from 0 to 1. And I'm plotting here the phase transformation. And you can see how it's distributed within your component. So again, phase field is a variable, a field variable like temperature. You can see how it changes from 0 to 1. So I'm just running that analysis, and I'm seeing how it evolves. And I'm plotting also the phase transformation. You can see how it's localized in certain regions. And this kind of localization of phase transformation is triggering some sort of toughening effect. So we see what we expect to see from experiments. And then one of the applications where we solve a variety of boundary value problems, you can find details on the paper. But one of the applications that these nitinol or the shape memory alloys are most widely used is biomedical stents, because you want them to, you want to crimp them first, you want to compress them initially, and then you want to expand them quite significantly. But you don't want irreversible deformations. And you also want a lot of basically elastic cyclic loading. So you want some sort of elastic hysteresis. So this is basically to ensure that you get blood. The blood is so sometimes the blood vessels can be blocked, and you unblock them through these stents. So you throw them in, you crimp it, then you deliver, you expand it post-deployment, and that way you open again the blood, and you enable the blood to go through, to flow through, and then you have basically, the first step is a compressive step, a crimp compression, then deployment expansion, and then as you flow the blood, you get systolic and diastolic compression and expansion. So you want to work with these materials because you don't want irreversible deformations, but you have large strains and you want them to be elastic. So you want to take advantage of the superelasticity effect. That's why they are so popular in the biomedical industry. But of course, they suffer from fatigue. So I will discuss about facial fatigue later on, but as you know, we can do facial fatigue. So this is work that I did when I was at both Cambridge and Imperial, and Lindsay Morris was at Cambridge. So basically, this is the idea. You can simulate in Abacus, this is Abacus, or any other package. You can simulate how all these processes of systolic compression and tension, and then you can see how this cyclic loading, how you start generating damage, and how you eventually propagate cracks and so on. That's the idea. Okay, we're going to move to ice sheets and glaciers.
So what was the new variable then?
Say that again?
One new variable was shown.
Yeah, so the variable that I showed here, this is the I'm not solving for this as a variable, it's a state variable, so you could think of, I don't know, like the flow stress or the current yield stress. It's a variable that is updated locally. This variable, I didn't include a lot of equations on this because I thought it would make it too dense, but this variable is the Martenside phase fraction. So there's constitutive models that tell you, depending on where you are here. So for example, that variable is 0 when you are in the austenite phase, but here it starts becoming non-zero, and it becomes 1 when it's fully transformed, and then it becomes again, goes back to 0. So you can see here, this is that variable. It's a variable that tells you whether you are in the martensitic or austenitic phase. That's the idea. And it's a variable that in this case we solve internally. You could solve it as a phase field as well, as an extra phase field, and some people do. But in this case, we solve it internal as a state variable. And that tells me a little bit, think about it as plasticity, basically, how much plasticity you have, how much this transformation in elastic strain you have, and that governs how much of the plastic dissipation and toughening you get. That's the idea. So it's a similar model that you showed before. The only difference is that we have a material model that is this kind of shape memory alloy material model. That is not too different from a plasticity model from a conceptual perspective. There was another question. Yeah.
So following up on that question, so we have two evolving fields here, right? So one is the phase field,
Mm-hmm.
the other is the phase fraction. Do you also confer the stress due to the formation of those phases?
Yeah, so the constitutive model, I didn't include equations, but the constitutive model is such that depending on this, think of the yield stress. So the yield stress has an initial value, but then as you keep hardening your material, you're changing your yield stress. That will have an effect on your hardening will have an effect on your constitutive Jacobian, but also on the stresses. Similar thing. So there's this Lagoda's model or the Riccio and the Sousa model. Those models will have different constitutive equations telling you how the stresses evolve, such that you can capture this basically. That you can capture that as you get the phase, I mean this is 1D, but also in 3D, as you can capture that once you reach a critical, so these are input parameters into the model. You need to tell the model what temperatures this phase fraction happens, what stresses this phase fraction happens. So you input those parameters into the model, then eventually you reach to that point, eventually you trigger that beginning of that phase transformation. based on your constitutive choices, you define how fast this phase transformation happens so slowly, like you're hardening in a way, and then eventually when you come back and so on. So that's what drives the evolution of this variable. And then this, in phase field there's no extra couplings with the phase field. So everything happens in the constitutive modeling point of view. You could have an extra coupling. You could say that the driving force is not only the strain energy density that is elastic, but also the transformation one that is associated with transformation strains. Or you can leave it as it is. In both cases, phase field will be able to capture the fact that these transformation strains are bringing some toughening into your material, which is the main observation in fracture with these materials. And this is what we see there. Yeah. Okay. So the next application is ice sheets and glacier. This is a beautiful problem to work with. So there's a lot of people interested in this. Basically, what glaciologists have concluded is that nowadays, back in the day it was a bit different. You had to do more with the temperatures of water. But nowadays, the main contributor to sea level rise is fracture, or what they call iceberg calving. So basically, an iceberg detaching from the sea. Because the ice is basically doing a bust stretching effect, so it's holding back the transport of ice and so on. And of course, this is a problem that difficult to tackle experimentally. This is the scales that are involved in this are very large. You can see here, look at the scale. This is 10 kilometers. So these are very large cracks. And there's a lot of observations, of course. NASA, the European Space Agency, others, they make a lot of satellite observations. So we have some data on when those cracks propagate. But it's important that we incorporate, if we want to predict sea level rise and therefore the impact that climate change will have, it's important that we develop physically based models that can capture this type of complicated phenomena. So let me tell you a little bit of the problem. So the problem is as follows. Let me first familiarize you with the terminology. So we have here an ice sheet. This could be, I don't know, Antarctica or the South Pole, or the North Pole, whatever you want. In this ice sheet, what you have is something that we call the ice shelf, where you have ice on top of the seawater. And then what you have is some areas where you have water, melt water, and then crevasses. Crevasses are like of cracks. These are crevasses with melt water. So you can see pictures here. These are the crevasses. These are dry crevasses. There's no melt water. These are wet crevasses. They are full of melt water. And then eventually you get the growth of those crevasses, those little cracks. Well, not little, those gigantic cracks. Eventually they grow. And then when they grow all the way through the ice shelf, so they go all the way from here to here, then you get a detachment of the ice, and then this is what we call iceberg calving. Then you get this ice floating there. So this is what we're trying to predict. By the way, you can see that you have basal crevasses are the ones at the bottom, and then you have also some surface crevasses. And then this is a hydrofracturing process because effectively what you have is that with climate change, you have higher temperatures. Higher temperatures lead to more meltwater, and you will see later the meltwater acts as a tensile stress, so drives the fracture basically. So the question here is, okay, if you increase the temperatures by this amount, how much extra meltwater would you have? And based on that extra meltwater, what will happen to your cracks, to these crevasses? Will these guys grow? Will they remain the same? Would you have this iceberg calving process? Will they go all the way down? This is, by the way, a crevasse, so you can see these are big cracks. And this is what people have been doing quite recently. This is a Nature paper for some years ago. This is a group in Columbia University in the US. So what they did is they mapped the entire Antarctica, and they used very simple fracture mechanics, what we saw on the first day. They said, okay, because I should say that, there's a lot of ice sheet models that kind of simulate those things. The ice sheet models that we use to predict sea level rise. But as you probably have seen from the news and also in the scientific literature, there's a bit of a debate as well on how much sea level rise will occur over the next century. Some of that debate is related to how much the temperatures will increase, but even for a given increase in temperature, there's a bit of a debate on how much will happen. It goes all the way from 0.5 meter of sea level rise, which will impact some people, but not that many people, to 8 meters, which will be a problem for a lot of people, including India, Spain, where I'm from, and the UK. Why people discuss going all the way from 0.5 meter to 50 meters roughly depends on the fact that we don't understand very well these iceberg calving processes. So all these ice sheet codes that NASA has, for example, they assume mass loss based on some coefficient that is basically, there's no mechanics in there. They're fluid dynamics codes, and they assume mass loss based on a coefficient that is based on historical observations. But there's a lot of people saying, oh, you may have various instability problems, a situation where you have multiple cracks propagating in cascades, so that will increase the sea level rise significantly. So we need to bring down physics. We need to basically understand a bit more whether cracks will grow or not with mechanics. We cannot just rely on historical data. So this is what some of the people have been doing. This is a paper in Nature. So basically what they did was to map the entire Antarctica. From observations, they know the length of these cracks, of these crevasses, and then they basically calculate the stress intensity factors. And they say, okay, they apply superposition. When you are dealing with linear elasticity, you can apply superposition. And for here, they have some sort of creep models as well, so that's up to discussion. But anyway, you apply superposition. You have a crevasse. Someone tells you your temperature is going to grow by this amount. Therefore, you say, okay, if my temperature is going to increase by this amount, I'm going to have this extra meltwater. So they put this extra load due to the meltwater and their stress intensity factor. They compare all the fracture toughness of ice, and they did it for every point here. And they concluded that, these red areas are vulnerable. These areas in in yellow and green are okay, so they will propagate, but they will not propagate until the end. And here nothing will happen, and so on. So this is they basically map the entire Antarctica. And linear elastic fracture mechanics is okay. It's not about approximation. But here we have creep. So that is a history-dependent problem. No longer we should apply superposition and so on. And we have other phenomena. So we try to go a bit beyond what these people have done. But this is fine. This is good stuff. So what we try to do is to develop a phase field model for ice sheet fracture. It has multiple ingredients, some of them which differ from what you've seen before. So maybe I'm going to start from the bottom first. So we have a constitutive model for ice that is kind of a power law creep. So this is what they call Glen's flow law. This is what the glaciology community uses. This is how they think ice behaves. They do experiments in the lab, and they conclude that ice behaves like this. This is Glen's flow law. So this is a power law creep, basically. So that's for the constitutive behavior. Then the phase field equation is the similar as before. The only thing is that, well, you have viscoelastic or viscoplastic strains due to the creep. We do also have inertia. We account for the role of inertia here. So you can see it's just the balance of linear momentum with the acceleration term. And the dots should be on the U, not on the rho. I don't know what that's coming from. Anyway, this is density, force equals mass by acceleration. Just the balance of linear momentum. We use poroelasticity, so this kind of poro mechanics description of an effective stress, to basically define three regions: the intact ice, the water field fracture, and then the ice fracture interface, where you have some areas where you have some pores and basically they're full of water. And then you have the air. And then basically we change a little bit the phase field fracture model. We use, I told you before there were multiple models, 81, 82, phase field inclusive zone. This is one of those models, more like phase field inclusive zone. So it's based on a critical stress. The reason why we use this one, I actually like very much the conventional one because it's based on Griffith. The reason why we use this one is that it separates a little bit the length scale from the fracture properties. And in this case, I needed to do this because the length scales involved in this problem are very, very large. Remember, if we go here, this is 10 kilometers. So if the length scale of my ice is 1 millimeter, then I'm going to have a big trouble meshing something like this. It's going to be impossible, basically. So I deviated a little bit. It's kind of the price you need to pay. So I use this kind of a stress-based phase field fracture model. And then we model a number of problems. So the first one, we're looking into the growth of a single crevasse. So this is the problem that you have, basically. This is the simplest boundary problem you can think of in 2D. So you have this ice sheet. Then you have the ocean here. So this is just a load here that depends on the ocean. And then what you have, so this is a compressive load that is closing the crack. The ocean actually doesn't want you to crack your ice sheet. However, the meltwater that you have here is applying a pressure, so you get some tensile stresses in the tip of your crevasse due to the meltwater. So it's a competition. And you can see here the stress field, right? So this is for a land terminating glacier, and this is for an ocean terminating glacier. You see that you go from a region, the red is tensile stresses. So your crevasse is in a region of tensile stress. So initially your crack wants to grow, but then eventually it's going to find a region of compressive stresses. So eventually your crack is going to stop. And even more for the case of an ocean glacier. Well, the tensile domain is very small, and quickly you jump into a compressive domain. That's why these things don't typically crack. That's why the icebergs don't typically detach. You don't have ice detaching, icebergs forming. The reason is that because of climate change, we get more higher temperatures, therefore we get more meltwater. So this meltwater will facilitate the fracture. So it will be a competition between these tensile stresses and the compressive stresses that the ice is seeing due to the ocean. So this is what we do. So we run the phase field simulation. Again, very simple. Same model as I showed you before. You just add the viscoplastic model, the Glenn flow law, and you have something like this. If I run it again, so the crack grows and eventually stops. Here, because of the compressive load, I don't have enough meltwater, it stops. So we can plot the normalized crevasse depth. So 1 means you got the full iceberg calving, the crack grow all the way through the ice sheet, versus the meltwater depth ratio, right? And as we have more climate change, we will go more toward this x-axis. And we compare with the finite element solutions, with the linear elastic fracture mechanics solutions, which you can compute just by computing, stress intensity factors here and comparing. And we can see that actually phase field is in good agreement. One has to use a Poisson ratio of 0.5 for the linear elastic fracture mechanics solution, because even though the ice has a Poisson ratio of 0.35, you do have, due to this Glenn's flow law, some sort of incompressible behavior. So due to the creep, you have incompressible behavior. So my phase field calculations, I can use the real Poisson ratio, and phase field will account for that incompressible behavior. But in linear elastic fracture mechanics, I do need to put a fake Poisson ratio that accounts for that. But when I do that, linear elastic fracture mechanics captures that well. And of course, what you see is, as you expect, if you have very little meltwater, the crack will grow but stop. As you increase the meltwater, you increase the load inside of the crack, and then eventually you get the situation where the crack will just grow through the entire ice sheet. This is fine, but we didn't need phase field for this. Linear elastic fracture mechanics did a good job. So the idea now is, what can we do to go beyond this, right? What can we use the phase field for? One is that we may want to see how multiple crevasses interact. If you go to reality is much more complicated than a single crevasse. You can see it here, you can see it here, multiple crevasses interacting with each other. So reality is much more complicated than this. So let's see if we can go beyond what the community is doing. We're using phase field. So here you can see the interaction between multiple crevasses. We do this, of course, for multiple spacings and so on. So there's a bit of shielding. You can see that the crevasses on the edges go a bit faster, but for this spacing, there's not much shielding. And we can compare this with a model called the night zero stress model, which is based on just computing stress fields and determining when the stresses become compressive. And we can see that we get actually a relatively good agreement, depending on the height of the ocean and the meltwater ratio. So we seem to be getting a good agreement. Then the other aspect that we have is floating ice shelves. So these were grounded ice shelves, but we can have floating ice shelves where we can have these basal crevasses in the bottom and the surface crevasse in the top. So again, you have a bit of a funny boundary condition here, but you have some Robin type boundary conditions to capture the buoyance pressure on the vertical displacement. But otherwise, it's the same problem. Again, you capture this with phase field. You can also capture it with linear elastic fracture mechanics, and again, we get a relatively quite good agreement in terms of the normalized crevasse depth versus the meltwater ratio at the edge and near the center. So you get different behavior depending on where you are. But what we can do with this is also something that you cannot do with linear elastic fracture mechanics. We can look at the interaction between crevasses. If you have a basal and a surface crevasse, what are they going to do? Are they going to make the fracture more easily? That depends on the spacing. You can see here how they interact, or sometimes they don't interact with each other, depending on the mixed mode conditions near the crack tip. So we can see, for example, we learned that the final depth of the surface crevasse is almost insensitive to the presence of the basal crevasse. We know that the depth of the basal crevasse increases with the separation to the surface crevasse, and we know that the basal and surface crevasse do not coalesce with each other. That's the idea. We can also model more realistic cases. Again, something that is more difficult to do with LAFM. So we take a glacier, a particular glacier, the Helheim Glacier. We can, from observations, from field observations, we can infer what is the basal topography and the surface elevation. This is the seawater. And then we can model the nucleation of crevasses. So we can model the creep. We can assume that when we reach a critical creep strain, damage will initiate, and then we can model the fracture. You can see here the damage nucleation due to creep, and now you can see here the evolution of the phase field and the complete fracture of the crevasse. So this is the idea. First, you model in this realistic configuration how those crevasses nucleate, which happen in areas of high surface gradients near the calving front, and then you can see how you get a little bit of some swallow crevasses growing away from the calving front, but near the calving front, you get significant damage. That's the idea. And we can also do 3D. There's a lot of interest in understanding not only in 2D, but what happens when you have a 3D crack. And we see exactly what they see in those field observations, that those crevasses grow up to a certain point. Then, because of the compressive stress state, they stop, but then they start growing in the horizontal direction, right? So you grow the crevasses a bit here, then it stops, but then it will start growing and they interact with the other like this. So the mixed mode condition, and this is exactly what we see. We have some field observations and pictures. I don't know if I put it here. I didn't put it, where we can do this. So basically it allows you to, it's a model that agrees with linear elastic fracture mechanics, so you're in agreement with what the scientific community is doing. But you can also use it to model more complicated scenarios, 3D, 2D, interaction of multiple crevasses. And one that we were particularly interested in was this marine ice cliff instability. So I said before, people are discussing whether the sea level is going to grow by 0.5 meters or 50 meters. And this is mostly related to this phenomena like marine ice cliff instability. So glaciologists, they argue that these things have happened in the past, so they may happen now. But all the discussion in the glaciology community is based on data, right? So they have some historical data and they say, this phenomenon happened a long time ago. We believe that today we have situations similar to the scenario where this happened many years ago, millions of years ago. So the question is, will it happen again or not? And I think we should look at this problem from a mechanics point of view. And the idea of this is that if this becomes, this ice cliff elevation becomes sufficiently large, you'll have a collapse mechanism where this will fracture. And once this is fractured, you expose again a very tall piece of ice to the sea. And therefore, you have this kind of marine ice cliff instability driven runaway retreat. So things are failing in cascade, one after the other. And if this, catastrophic collapse mechanism happens, so this was published in Nature some years ago, and it's been debated among the glaciology community. If this thing happens, if the ice by its own weight causes this damage, then it will be catastrophic because we'll lose a lot of ice. But whether it will happen or not is unclear. And we have looked into this problem basically with phase field. And the critical quantities that you're interested in is basically what is the elevation at which this phenomena will happen, how tall this thing has to be. And basically you have, there's some uncertainties related to the boundary conditions. We can limit those uncertainties in two cases, the free slip case and the frozen base case. And in between you have something called the Wedman sliding law, which is some sort of Robin boundary condition that you apply here. This is the friction that you get in there. So we look at a glacier of height 135 meters, and you can see this is the phase field evolving, so there's lots of damage here. This is a bit of a challenging problem, by the way, from a computational perspective, because normally we neglect the gravity loads. We normally, our gravity loads are quite small in any engineering component that we think of, but here, because of the very large scales involved, gravity loads play a big role. So you have a situation where, that's why we also have the inertia here. So inertia, sometimes inertia is important, sometimes you don't care about inertia, but inertia can also help regularizing convergence. And here the challenge is that if you think of a gravity load, think of a force displacement curve, you are somehow telling your component that your gravity load is, it remains constant or in time. You have a load that is being applied, but your material is losing stiffness. So somehow your gravity load has to go down, but you are at the same time telling that gravity load to remain constant. So it's a bit of a challenging problem from a convergence perspective. So you see here quite a lot of damage evolving, and you can see that, depending on whether you consider free slip or low basal friction, you do prevent ice calving, but you get a lot of crevasses developing away from the terminus. So you can see here a complete failure. And then you can also look at this friction coefficients, that are more realistic coefficients that we know from observations. So we can see that, how you eventually create these cracks that eventually nucleate and you get the complete calving. So basically then we can change the height and determine under which conditions this kind of damage phenomena are going to happen. Okay, so that was all on ice sheets and glaciers. Some examples of hydraulic fracture. So again, we need to change, question.
Clarification. You were mentioning about the Poisson's ratio and the modification from 0.5 to 0.3. It isn't clear to me when it's an incompressible material.
Yes, so it's a linear elastic material that undergoes creep at some point. So then when people use linear elastic fracture mechanics, they need to pick a Poisson ratio to calculate the stress intensity factors and so on. So they normally will pick the one of ice, which is 0.35. However, ice actually, what we see in these models is that it's behaving as an incompressible material because you have this creep loading. So what we basically say is that our constitutive model captures naturally that, like if you do plasticity. So you would, if you have a linear elastoplastic material model, you would define your Poisson ratio at 0.3, but then your material will behave incompressible in the plastic regime because of the constitutive laws. So the same goes here, because you have the creep law, it's going to behave as an incompressible material. What we're saying to people is that if you do linear elastic fracture mechanics analysis, make sure because the straight state is such that creep is dominating. Make sure to pick your Poisson ratio to be equal to 0.5 to capture these stress fields that come from this incompressibility as opposed to the ones that will come from a linear elastic material with 0.35. Yeah.
There's not necessarily a follow-up, but for the same system. Ice is extremely isotropic, right? I mean, to what extent do you think we are actually making the comparisons valid? I'm assuming that most of this analysis was isotropic.
Yeah.
So are there things that you can still capture because it's hexagonal with extreme anisotropy?
Yeah, and I think in the ice, that's a very good point. And in the ice community, there's been kind of two trends. So there's some people that have been doing very careful experiments and looking carefully at the ice, how it behaves. And then separate from this is the glaciology community, which I don't want to say that they're not careful. They are careful, but they are looking at a very large scale. So they need to do simplifications. And there must be a sweet spot there. We look a little bit into the anisotropy. We didn't see that much of an effect. We did see a big effect because here these crevasses we're talking a half a kilometer. So the temperature, the ice behavior, so the properties of ice will change also. The ice that you have near the surface is very different than the ice that is compacted millions of years ago that is at the bottom. So we did change, we did a paper I didn't include here, but we did change, the temperature also changes along this half a kilometer. So we did change properties and temperature based on these through thickness evaluations. And I mean, we don't know that much about how the ice is different, but we know a little bit. So we do change, and we did see quite a an effect in this phenomenon. So I think it's an important factor. And in fact, I haven't done it, but I have on my to-do list to reproduce that Nature paper considering this. And I think they will be. So I think there's a lot of things that can be done. Anisotropy, we only look at it briefly, but maybe it's something interesting. And this kind of Antarctica Nature paper is not that complicated. It's a lot of treatment of data, but it's basically a stress intensity factor calculation, comparing against toughness. So one could do all those things, reproduce those things, adding your anisotropy, adding the thickness dependency of properties of ice. So the field has just started in a way. So there's still a lot of things for grabs there. Yeah, not for grabs. Yeah. So the other one, the third application I want to see today was hydraulic fracture. So hydraulic fracture, again, we have a poro mechanics description. So those of you working on solid mechanics and hydraulic fracture will remember this. This is an effective stress. You talk about the skeleton, you have a porous material. Then you have the facial fracture, same as before, no difference. And then you solve for an additional equation that is Darcy's law. So you want to figure out the fluid pressure, the fluid velocity, and so on. So the fluid flow. How we do that in practice in Abacus with a UMAT, now we need a UMAT HT. I will discuss that at a later date. There's a date that we talk about all implementation. For the time being, the key point is that facial is very convenient to use with multiphysics problems. So you can easily combine these equations. And then the only thing is that, of course, these equations that you have in Darcy's law, some of the parameters will have different values inside of cracks and outside of cracks. So you need to come up with a way of interpolating those values. But since you know the phase field, you can use this type of reservoir transient fracture domain decomposition approach, where you basically have this auxiliary field. So you have this variable that tells you, okay, based on the phase field, I'm in the reservoir domain, I'm in some sort of transient domain, or I'm inside of the fracture domain. And then you can define all those coefficients, so the storage coefficient, the Biot's coefficient, porosity, permeability tensor, as a function of those coefficients. So basically, you're using the phase field to interpolate. Anytime, think of thermomechanical cracking. Maybe you have conductivity inside of cracks, maybe you don't. If you don't, then you can always use the heat transfer equation and say the conductivity will depend on the phase field, and it will be 0 inside of cracks, 1 outside of cracks, and something in between. So some sort of interpolation measure. Since the phase field tells you where the crack is, you can easily solve the problem and solve the whatever extra equation you have, in this case Darcy's law, accounting for properties that are changing in space based on the phase field. That's the idea. And then, well, this is some representative example. So in this case, here I'm plotting the fluid pressure. This is what you're solving for. You can see that it's increasing inside of the crack. Here, basically, there's two cracks. I inject fluid inside of the first crack. The first cracks are growing. The second crack is not exposed to the fluid until the second crack becomes into contact. So you'll see the first crack is growing, the second one is not growing. There you see they connect to each other, and the crack starts to grow. And this can be very powerful in the hydraulic fracture because hydraulic fracture is a complicated phenomena where you're injecting a fluid. The cracking phenomena is very complex. You have crack branching, coalescence of multiple cracks, and you have this interplay with the fluid pressure. So, and this can be naturally captured in phase field. Again, no convergence issues, quite nice calculations. No, this is also outcome of simulations. So there are some experiments, and let me see if no, I don't think, I'll show you a boundary value problem where we validated against experiments. It's tricky sometimes to do this kind of experiments, but people do have experiments where they inject something and they see multiple cracks going, and so on. But this is all, so this is the fracture and this is the pressure, this is all simulation. Yeah. This is another case study, if I remember well, where we have, again, a crack with fluid, another crack sitting down there. This is another classic benchmark in the hydraulic fracture community. So you can see that you're injecting the fluid in the inner crack. That crack starting to grow, and then eventually when it grows sufficiently, it interacts with the other face field, with the other crack, and then the both cracks grow. So I guess the point is that you're capturing this interplay between the pressure and the fluid and the crack, basically.
The pressure, right-hand side, what is evolving is the pressure, right?
Yes. So think of a fluid. Basically you're growing cracks because you're injecting a fluid at a very high pressure inside of a crack. So that is going to lead to tensile stresses. So you are similar to the hydraulic fracture problem, the glaciology problem, right? You had a crack that was growing due to the fluid injecting some tensile stresses. So this is the way they do hydraulic fracture. They inject a fluid that is typically water plus some other components that grows cracks. So you can see that how basically what we're showing here is that by injecting the fluid, this crack in the inside is growing. Eventually this crack has no fluid, but when the two cracks go together, the fluid goes through both cracks and then you start seeing both growing along.
They became analogous, that's when you get to show this.
Say that again?
These two are behaving in an analogous manner, which is why we are showing this.
Yes, so I want to show that the coupling between the facial fracture and the pressure, fluid pressure, is working well, in the sense that you can see how as the pressure, we increase the pressure, the crack starts to grow, the pressure goes along with the crack, the fluid pressure goes along with the crack and eventually expands into the new crack and grows.
The static liquid, right, to which you are using another liquid.
So in this case, Darcy's law is based on laminar flow. Some people argue that in hydraulic fracture you have actually turbulent flow. So they have more complicated models where you could combine this with a more complicated fluid dynamics description. In this case, Darcy's law is based on laminar flow. Yeah.
So here, what is the loading which is actually driving this propagation of the crack?
Just the fluid pressure. So you can define a fluid pressure. So because you are solving an equation for the fluid pressure, you can define a fluid pressure. So you can inside a right-hand side, this is like a source term that will be like a flow rate. So you can define your flow rate of the fluid, and then you can grow the crack. So this will, of course, lead to, so there's a coupling here with the pore mechanics. So this will change your strains, and that will change your phase fill. That is the coupling. Yeah. And this is one that we compare with an experiment, but I don't think I included the experiment. No, I did not include the experiment. But this is a classic experiment where we got good agreement. We basically have a rock. This is an axisymmetric model. They inject a fluid. They have multiple injection points, and they try to see how those injection points correlate, and we get a good agreement with experiments. What you see is depending on the spacing, you get different behavior. But eventually you see all the cracks propagating, there's a bit of shouting effect, and some of the cracks interacting with each other. Let me just play it again. So again, 4 injection points, you are injecting a fluid, your crack is growing. This is abacus, by the way. You see, abacus, the temperature, the nodal temperature is NT, 1, this is the nodal temperature in abacus, so this is what we're plotting. And you see basically that it goes from 0 to 1, and that is changing, and this is the fluid flux, basically. So this is the idea. You just run standard abacus simulations, but your cracks are going to evolve between 0 and 1. Okay, so that takes me to the last element, and I have half an hour to cover this, which I think should be fine. Composites. And I want to cover 3 things. Functionally gray materials, which are arguably a type of composites. Fiber reinforced composites, carbon and glass fiber reinforced composites. And finally, carbon nanotube based composites, kind of smart materials. So functionally gray materials, this is a topic that interests a lot of mechanics people. Particularly, I think is quite popular in India. I think a lot of people like to work on functionally gray materials. Among others, because it's a topic that is interesting from a mathematical perspective. It's easy to, you do a buckling analysis, vibration analysis. Instead of dealing with constant properties, you change your properties of function space, and you can use the techniques and reapply your techniques and get an insight into this. But the idea is that basically these are materials where composition and properties vary in space. So for example, you have something like this, where you could go from, 100% metal to 100% ceramic. So you start in one side, or anyway, material 1 to material 2. You start with 100% material 1, you vary composition, until you get to 100. So you go from 99% material 1 to 1% material 2, 98% material 1 to 2% material 2, progressively until you end up being 0% material 1 to 100% material 2. So your properties vary in space. And these are useful, well, for mainly two reasons. Whenever you have non-uniform surface conditions, for example, there are components that are exposed to a gradient in temperature. So you may don't want to use a ceramic that is heat resistant throughout the component. Maybe you want to use the ceramic in the part where the temperature gradient is highest, or temperature is highest, but then change progressively your component to another more cheaper or more interesting component material in the side where you don't need such a strong, let's say, temperature performance. The other approach is to eliminate the stress discontinuities at interfaces. So for example, you see here, you have a heat-resistant ceramic coating and a metal substrate. If you don't have any sort of interface, you have a stress discontinuity because you have two different materials. But if you introduce a graded interface, then you have a much more smoother transition of stresses between one and the other. So these are basically the reasons why we want to use this kind of functionally graded materials, to accommodate non-uniform surface conditions or to eliminate stress discontinuities of interfaces. But these problems are interested in fracture, and the reason they are interested is that they bring mixed mode conditions inherently. So if you think of a plate with a crack in mode 1, this you would expect to be a mode 1 fracture. You would expect your crack to grow like this, and that's fine if you have an homogeneous material. But if you have a material where you have a special variation of material properties, for example, your Young's modulus is going in this direction, then if you calculate the stress intensity factors, you can do that quickly in Abacus, you will see that you don't get any more K2 equals 0. You get something that is non-zero due to the gradient in properties. This is Young's modulus that is varying in space. So due to the gradient in properties, you're going to get mixed mode conditions. So this crack will do something funny, and then eventually all cracks like to go mode 1 at the end of the day, so it will do something funny and then it'll go. And not only that's only if you consider the mechanical properties, but the fracture properties, of course, will also depend on composition, so they will also change in space. So your toughness is also likely going to go that direction. So your crack at the end may actually do something funny like this because it will deflect towards your more brittle material. That's the idea. So they're interesting because even in mode 1 fracture problems, we get mixed mode fracture problems. So we don't know where the crack is going to go, basically. That's the idea. So this is work that I did here with Sundar, Natarajan, and others. And basically what we have here is that we look into functionally degraded materials with phase field. It's straightforward to implement. The only thing you need to do is, remember we had a line before that said, and this was a question that I got in the break as well, how do you introduce a functionally degraded material in that UMAT code that you showed before? Well, the UMAT tells you the coordinates. So if you know how your Young's modulus or fracture toughness depends on the coordinates, then I can just add an extra line that says coordinate x plus something plus coordinate y will give me this value of Young's modulus. So it's one line of code, it's straightforward. And then this is what we get. So just to show you various examples, here it's a comparison with experiments on epoxy glass functionally degraded materials. You can see that the crack deflects. It's a 3-point bending test. In an homogeneous material, you would expect to see the crack growing in mode 1, straight ahead, but it's not. It's actually moving, it's deflecting due to this variation in properties. You should also compare, you can also compare with other numerical tools. This is a classic finite element benchmark. And you can see this is with remeshing, this is with some sort of X-fins, I remember well. So you can see that these other tools, they all get the same, more or less the same result. The crack deflects due to the functionally degraded nature of this material. But then you can see that phase field, different to the other tools, the calculation does not finish when the crack reaches the second hole. Phase field has the ability to predict the nucleation of a crack. So you keep loading, a crack appears there, the crack continues to grow, eventually the crack reaches the third hole, then you keep loading, a third hole appears, and then you get the complete failure of the. So different to these other methods, whenever the crack reaches the hole, the calculation is an end. We have the ability to predict the nucleation of cracks from smooth areas, like here, and then you can grow the propagation of the crack. So I think this is another classic example. But basically, this is the idea. You can capture well with experiments the crack deflection due to this variation in properties, and you can capture well also this kind of fracture property. And you can do it in 2D and 3D. So we have used this to develop kind of fracture-resistant materials. So some people say, okay, if we can change properties in space, maybe we can do something where we basically design a material where the crack will encounter a tougher material as it propagates, this is what you see here. So this is a 3D problem. This is the crack. This is done in Phoenix, so the crack was defined geometrically, so the crack starts here. This is the phase field. You see the phase field starts growing, but it's growing in a stable way. And how can it be that a situation where you have a mode 1 fracture, or mixed mode, but mostly mode 1 fracture in a linear elastic material, the crack is growing in a stable way? Well, the reason is that here we're introducing the functionally graded materials along the x direction, so along the crack propagation direction, which means that the crack as it grows is encountering a material with a higher toughness. So then even though it wants to grow, it does not grow because eventually it grows if you keep applying load, if you keep putting energy in there, but it's encountering a material with a higher toughness and therefore you slow down your growth. And we also did other cases. For example, you vary the properties along the thickness direction, and then you can see how the crack starts to grow in the corner that is weakest, and then eventually you get this unstable crack growth. But you see you can get convergence quite nicely, full fracture propagation in 3D. Convergence gets quite nicely captured. You can see this starts here on the corner, which the toughness is weaker, but then eventually expands through the entire domain. And this is the kind of force displacement curves that you get. So you get, this is the homogeneous response, and then depending on what you're after, you could design a material where maybe you wanted to, you don't mind about the peak load being lower, but you want to see a stable crack growth fracture because then that allows you to replace your component. You can see it with your own eyes that is damaged. You can replace your component as opposed to catastrophic failure, or you want to do a functionally graded material where you want to increase your load carrying capacity and you don't care about the failure that will happen because you are sure you'll be moving around somewhere here. So this is the kind of games you can play where you vary the properties in space, the composition. And I didn't discuss much about how you would implement this, but it's straightforward. You just, in the UMAT, you just change the Young's modulus as a function of space, or the toughness, any property that you change as a function of space. And this is where we use the adaptive remeshing that we discussed the other day. Again, because we don't know where the crack is going to grow, because of these mixed mode conditions that come with the functionally graded material, then we want to use this kind of technologies to minimize the cost. But we discussed that the other day. Okay, so let me go into composites. So this is work that I did with my close collaborator, Wei Tan, who is an academic at Queen Mary, University of London. So we were colleagues at Cambridge before, and back then, when we were colleagues there in Cambridge, no one had used phase field to model composites. We started working on it, and another group also in Spain, from Seville and Girona, they published something, but they were looking all at the macro scale. What we were interested was in the micromechanics of composites. So we were the first to look into this composite micromechanics fracture with phase field. So the idea here is that we have basically, we're going to resolve the fibers. So you have a matrix, then you have some fibers, and then 3 fracture phenomena can happen. You can rupture the fiber, you can rupture the matrix, or you can debond the fiber from the matrix. So in the first paper, we decided to use cohesive sum models to debond the fiber from the matrix. So everywhere we had fiber matrix, we put a cohesive sum model based on this linear attraction separation law given by attraction and energy. Later on, we decided to do it with phase field because it's the same thing, and I'll show you later. We can also tell phase field that they can only move in certain locations, although interfaces have different properties at the bulk. I'll show you later how. And then, so this is the other approach. This is what I say. So you could model the debonding. If you think of the debonding, you could model with cohesive elements. This is what we did at the beginning. But you could also do it with phase field, because you can have an equation like this that you run as a pre-processing step, where you basically use this extra phase field, or this pre-processing phase field, to interpolate properties between the interface and the matrix. So you see here, we want to assign different properties to the fiber, to the matrix, and to the bulk. And this is the GC. You see how the GC changes in space. So we basically use the phase field equation to, you could use any equation that you want. You basically interpolate the properties, and then your GC is going to depend on that pre-processing phase field equation. So you have a toughness of the interface. You know the toughness of the interface. You know the toughness of the bulk. You know the toughness of the fiber. So you basically interpolate in between. That's the idea. It's a pre-processing step. It's straightforward to do now because we have provided the code as well, in case you're interested. But anyway, both ways work okay. I think we move to fully phase field. In the first study, we did phase field for matrix cracking, fiber cracking, and cohesive zones for debonding. But then we saw sometimes a bit of convergence issues, so we moved to fully phase field. But again, both options are fine. And I think one could argue that actually this description of a smooth interface is physically sensible, because when we look at the microscope, it does look like, the change between fiber and matrix is not completely sharp. There's some sort of interface where we see a mixture of both components. So this is, for example, the first experiment we did. So this was experiments done by a group at IMDEA Materials. So they did 3-point bending on these carbon fiber reinforced polymer composites. And of course, we didn't decide to model the entire sample. We didn't model the micromechanics of the entire sample because that would be too expensive. So everything we assumed was homogeneous everywhere, except for a region in front of the crack, where, based on the experimental images, we incorporated in our finite element the fibers, the matrix, and their debonding. So this is what we got. So we run the simulation. On the left, you see the experiments. On the right, you see the simulation. So basically, what I'm doing here is I'm telling Abacus when phase field is larger than 0.99, remove the material. So you see here how the crack grows. You see multiple things happening. You see that more or less the experiment and the model are in relatively good agreement. So they're supposed to run at the same time, more or less they reach the same profile. So what you see in the finite elements is multiple things happening. So you see here, there's some debonding. Some fibers are debonding. You also see there's some cracking of the matrix and the growth of cracks to those fibers debonding on the matrix. And this is exactly what you see as well in the experiment. Right? Propagation of a crack through the matrix and some debonding between fiber and matrix. You can see here a comparison with experiments for different levels of applied displacement. So initiation of a crack, you see there seem to be in good agreement, and then the propagation of a crack. And you can see there's a bit of debonding, those fibers and matrix have debonded, and there's also a crack growing through that interface. And then when we plot the force displacement response and the R curve, we capture what you see here. So this is the force displacement response. Again, seems to be in good agreement with experiments. These are all, the black lines are replicate experiments, so they did multiple experiments. They get a bit of scatter, not too much. And here, this is the R curves, the J versus crack extension curves. Again, we see relatively good agreement in experiments and modeling. So we're quite happy about that. And then what we can do, yeah.
So I'm just curious, did you take the image of the composite and mesh it as is, or you just assume that it's a random arrangement of the fibers?
We did random arrangements of the fibers, and then we look and see whether it was similar to that.
Not the image-based meshing?
Yeah, because they also did multiple tests and so on, so it's a bit, so it's not identical, but it's similar, I would say, yes. So I think we ensure the same fiber matrix composition, so the same volume fraction of fibers, basically. Yeah, and then same dimensions of the fibers and so on. Yeah. And then what we do is, once you have a model that you can trust and you feel it gives you the same conditions as the model, then we start to looking into things. For example, during the manufacturing of these composites, you often induce porosity. And there's been a bit of a debate in the community whether pores are good or bad. In general, pores are bad. But people argue that sometimes you get a bit of crack blunting due to the pores and so on. So we added those pores, and we tried to simulate what happens. You can see different volume fractions of pores. And someone yesterday was asking me, I'm working with some porous materials, 3D printed materials. What do I do with the pores, right? You could put them, as some sort of phase, or let's say, state variable, some sort of field variable, or you could just define them explicitly if you want to deal with the micromechanics. If you know your porosity well, you can add it in there and see what happens with your crack. And I've seen people doing that in the context of 3D printed materials. And then, my colleague Wei Tan, he was interested in also this kind of bio-inspired composites. So he said maybe we can define composites where they have some sort of brick and mortar microstructure, grain bridging microstructures, and see whether cracks behave or how do cracks behave. So once you have a virtual tool that is modeling these problems, then I think you can do anything you want, basically. And again, there's not a lot. The information that you need here is, mechanical properties and fracture properties, which are strength and toughness of the fiber and the matrix. And the interface, of course, the debonding one. That's all you need. So this was the first paper that we published in this, and maybe because it was the first to apply phase field to micromechanical composites, it has been very heavily cited. But the one I actually feel the proudest is the next one that we did, because what we did now is to take it one step further and do 3D. So now we model kind of the same experiment, but 3D. We have the fibers. You can see the whole fibers. And the beauty of doing it 3D is that you naturally capture the fiber bridging effect. So all the literature I have seen before was showing, so basically what happens when you have fibers, right? So this is exactly what you see here. You have a crack, The matrix is relatively brittle, so if you just had a crack in a matrix, the crack will just grow like this. Mode 1, you have, this is R curve, so J or K, so some measure of the applied load versus crack extension. You will just get something completely flat, unstable crack growth. In composites, good for us, they have good fracture toughness. You have a fiber bridging effect, so you have these fibers that are bridging the crack, they're closing your crack, basically. So because those fibers are closing your crack, you get a toughening effect, which is good. You know, we get an engained fracture resistance. But all the models that I've seen so far, what they did is first they ran an experiment, and then they had some sort of fitting of that toughening effect, and they embedded that fitting effect into the model. And that's because you know it will give you the experiment under the conditions of the experiment. But if you're looking at a different component where there could be other things playing a role, then you're going to get a slightly different response. You need to make sure that you're always small scale yielding and other things. So my goal was, what if my model can tell me what is the bridging effect? And in order to capture the bridging effect, what I need to do is, I need to model those fibers. I need to model how those fibers close the crack, and I need to model eventually how you eventually fracture those fibers and the crack is free to go. So this is what we decided to do. So we did these 3D calculations where we put the fibers. So we are simulating the fracture of the fiber, we're simulating the debonding, we're simulating and you see here what's happening. So this is a 2D representation of the 3D problem. So you have some fiber bridging effect, the crack is being slowed down due to the fiber bridging, but eventually you're rupturing those fibers and the crack continues to grow. You get some debonding as well between the fibers and the matrix. So all the phenomena are being captured. You can see the debonding here between matrix and fiber. And eventually you get basically, for any choice of fiber volume fracture and any choice of whatever you're interested in, you can capture naturally this kind of R-curve phenomena. And you can see, for example, that the finite element prediction is very different from the rule of mixtures. So rule of mixtures will do an interpolation between the fibers and the matrix. You can capture this toughening effect associated with the fiber bridging. So I was actually quite excited about this because all the things that I've seen before was you do an experiment, then you fit an experiment. Here, you do the 3D experiment, so you know what is the effect of the fibers, and then you can change the volume fraction of the fibers, the properties of the fibers to see how much you gain. You can change, again, this kind of bio-inspired reinforced composites and so on and so forth. I don't think this paper has received the attention that the other one has received, but I found it was quite an important milestone. And then finally, we have a paper in preparation that has been in preparation for years now, but hopefully we'll finish it at some point. I think the first author became an academic and lots of teaching and admin, so we're still there. But that's where we have an elastoplastic behavior of the matrix, and it seems that we're getting good agreement with experiments. So this is digital image correlation, and we've seen that we are getting a good agreement with experiments here. You can see the experiments and the numerical modeling, and we are predicting cracking in those composites, accounting for plasticity as well. And then the last item of fiber reinforced composites, and maybe I'll leave the carbon nanotubes for tomorrow. The last item of the fiber reinforced composite is that we are looking into multiphysics problems. As I said before, we are kind of, in general, we typically understand quite well components when they are sitting on their own without an effect of the environment, but when the environment comes in, you get a much more complicated scenario. So the application is offshore wind energy, and you can see here that these wind turbine blades, after only 3 years, they are being degraded. And so this is a problem caused for the humidity. So we want to model the transport of humidity, and I'll discuss tomorrow how we do multiphysics problems like this. But I'll just showcase some examples so you can see that phase field is good at capturing this kind of phenomena. But basically the idea is that you can capture humidity effects, and it's still unclear in which way humidity interacts with, I think we need more experimental data with composites. There seems to be some good things and some bad things happening. But you can capture those things in principle. So you can come up with a formulation, this is a paper we published a couple of years ago. You can come up with a couple formulation where you have basically the deformation problem. You have the damage problem, which is the phase field, the one that we just discussed. And then you have the moisture problem. So you have a moisture transport problem. It's very similar to hydrogen. So this is the concentration of moisture. And the concentration of moisture evolves based on gradients of concentration. At the end, you want to have a uniform concentration. But it's also, when you have hydrostatic stress, you are expanding your matrix, and therefore more moisture can fill in. So there's a coupling with mechanics. This is what we call, the moisture redistribution. Then there's also another coupling with mechanics in that moisture results in some chemical strains. So you have these chemical strains due to changes in concentration of moisture. This is what we call the hygroscopic expansion. And then, of course, there's a coupling between the moisture redistribution and the damage in that, these strains will lead to damage, but also the propagation of cracks will lead to moisture redistribution and diffusion as you are exposing your sample to the outer surface, basically. That's the idea. So you can couple all of this. So basically you have one equation that you solve extra. This is the concentration of this moisture, relatively easy to couple. Similar to the heat transport problem. So again, if you have another way of adding an extra temperature, you can fake the temperature to be concentration. We'll discuss that tomorrow. But yeah, you solve an equal transport problem and everything is fully coupled. And just to show you some examples, so this is, you can find the details of the paper, but some different distributions of fibers and trying to understand how this mismatch in temperature or transformation will lead to some phase field damage. In this case, we're using phase field to model debonding as well, so we start seeing some debonding of the carbon, the matrix and the fibers. Again, we have another crack and we see the propagation of the moisture. Here you see the propagation of the crack, a bit of debonding, but mostly propagation within the matrix. As a function of time, of course, the moisture concentration, so we do calculations as a function of time. The moisture diffusion will be sensitive to time. We did it across multiple scales, so not only at the macro-mechanical aspect, but also the laminar case, and we deal with typical scenarios of boundary conditions typical of humidity, so you have some sort of absorption stage, some equilibrium stage, and then some drying stage, and you can see how the laminate behaves under each of those conditions. And yeah, this is basically some of the representative results. We have 10 more minutes left, but I don't have enough time to cover the carbon nanotube composites in 10 minutes. So maybe I think yesterday I stole a bit of your time. So maybe today I'm gonna give you back those minutes that I stole from you. Any questions so far? Okay, if not, you're free to go. I'll see you in the afternoon. And yeah, have a nice lunch.